Hello, today I'm going to teach you crystal field theory. This is a theory applied to explain spectral properties of coordination complexes. It is a theory which is intermediate between the earlier theories such as Werner's theory of coordination complexes and valence bond theory, and much more advanced theories such as molecular orbital theory. So let's see what crystal theory has in store for us. It is a theory which was put forth by several physicists. Noteworthy is the work of Hans Bethe, and initially they were studying coordination complexes in their crystalline state, and they were doing a number of experiments over their spectral properties and also included magnetic properties, and came forth with a set of theories which today we know as crystal field theory. Um, so there are certain assumptions that one needs to consider when we consider crystal field theory. The first consideration is, or the assumption is, that all the interactions between the metal ions and the ligands are electrostatic in nature. I just mentioned it. All the interactions between the metal ion and the ligands are considered to be purely electrostatic in nature. This was the original form of the crystal field theory. Later, people came up with ideas to include some amount of covalency. And to do this, the first thing that one needs to consider is that all ligands are considered as point charges. All ligands are considered as point charges. We know that ligands are electron-rich molecules, and they donate their electrons to the metal ions, and through which the mutual sharing, the bonding takes place. So crystal field theory states that in a coordination complex of a particular geometry, the ligands approach the metal orbitals in a certain geometry, and depending on the geometry, it interacts with the orbitals which contain the electrons. So particularly in coordination complexes of transition metals, we deal with d orbitals because they are the outermost valence orbitals, and they interact with the incoming point charges of the ligands, and the ligands are electron rich. And so what happens, depending on the geometry with which they approach, the d orbital electrons interact, and they get destabilized or stabilized with respect to the energy levels of the degenerate energy levels, and depending on the interaction, there will be a splitting of the d orbital energy levels into different sets, and based on these sets, one can easily interpret the spectral properties as well as the magnetic properties of coordination complexes. So let's take the example of coordination complex which has an octahedral geometry. So let's call the complex ML6, and 6 ligands are bonded to the metal in an octahedral in an octahedral fashion, or in an octahedral geometry. So according to crystal field theory, this geometry is easily visualized when you place a metal ion in the center, the body center of a cube, when you place it, and when one considers the ligands approaching through the center of each of the 6 faces of a cube, it is an illustration of an octahedral geometry. Right now I'm not showing I'm not drawing it here, but one can easily visualize with the idea that the metal is placed in the center of the cube and 6 ligands are approaching the metal in the center from the center of each of the 6 faces of the cube. And so what happens is that there are 5d orbitals that we all know. So namely dxy, dxz, dyz, dx square minus y square, and dz square. These are the 5d orbitals which are available in a transition metal, usually partially filled with electrons. And what happens is that these 5 degenerate set of d orbitals split into sets of different energy levels, and because of selective interaction with the incoming ligands. So in the case of an octahedral geometry, this is what happens. The 5 degenerate d orbitals get split into 2. Two different levels. One is having higher energy and said to be destabilized, and another set having 3 orbitals, and they are lower in energy than the starting degenerate orbitals, and they are said to be stabilized. So this set of 3 orbitals are given the symmetry label T2G, and the set of 2 orbitals which are destabilized, that is higher in energy, are given symmetry label E subscript G. So which of these 5 orbitals fall into each of these categories? So the 3 orbitals which fall into the T2G category are dxy, xz, and yz, and the 2 orbitals which fall in the EG category are x square minus y square and z square. Okay? Now the energy difference between the EG set of energy levels and the T2G set of energy levels is given the term delta O. O for octahedral, and delta is what is known as the crystal field splitting parameter. Crystal field splitting parameter. And usually this energy gap is measured in the units centimeter inverse, which is one way of expressing energy. In metal systems having only one d orbital, one d electron, this crystal field splitting parameter corresponds directly to the absorption maximum that one can see in the electronic spectrum of such a system. So let's take the example of a D1 system, that is a complex with the metal ion having only one electron. So what happens is, before the complex forms, this single electron is in one of the d orbitals. For convenience, I just put it here. And what happens is, when this splitting happens, this electron goes and fills up one of the stabilized orbitals. There is degeneracy within these 3, and there is degeneracy within these two. So one has to keep that in mind. And so this electron, again for convenience I just put it in xy, it can as well be in xz or yz. One cannot precisely say in which orbital it will be, but it will be in one of the T2G orbitals. So, so this will represent the ground state configuration of a coordination complex with 1d electron, and its electronic configuration now can be written as T2G1. Obviously Eg will be 0, so I am not going to mention that here. Now the electronic spectrum of such a complex can easily be explained when one considers that on irradiation this electron at the T2G level gets it makes a transition to the Eg level, and then when it and then after a while it will relax back to the ground state. So from a T2G1 configuration to Eg1 configuration represents the electronic transition which is responsible for explaining the electronic spectrum. Great. Now, why does this splitting even happens? This is a very important question, and the reason the splitting happens is because of the directional nature of the orbitals, the lobes of the d orbitals. So dxy, dxz and dyz are three orbitals which have 4 lobes which are directed in between the Cartesian axis. So that is a dxy orbital has lobes which are distributed in between the x and y axis. So it can be, for example, it can be represented like, if this is the y axis and this is the x axis, the orbital lobes are distributed in this fashion. Of course, the lobe should carry the parity. So this is how they are. And so what happens is, as I mentioned earlier, the how the crystal field gets generated as the ligands approach the center of the body center where the metal is placed. When you consider that, the ligands are actually approaching the metal through the Cartesian axis. And so what happens, these orbitals which have their lobes in between the Cartesian axis will experience reduced amount of repulsion because they are at an angle. The ligand is approaching through the axis and the orbitals filled with the electrons are at an angle. So they experience reduced amount of repulsion as compared to the other two orbitals which are dx square minus y square and dz square, whose lobes are directed along the Cartesian axis. So because of which the electrons in these two orbitals will experience greater repulsion. So we all know that when there is greater repulsion, there is greater energy, and so the system is said to be destabilized. And then relatively to that, this system is these orbitals are stabilized. And with respect to the energy level of the degenerate level, one can easily calculate that the destabilization is 3/5 delta O and the stabilization is 2/5 of delta O. Now this delta O is an empirical value which one may obtain from the analysis of the electronic spectrum. And as I told you, for a D1 system where only one electron is there without any possibility of inter-electronic repulsions in the d orbitals, this delta O directly corresponds to the lambda max that one may see in the electronic spectrum. Okay. Now, I showed you a representative idea of a dxy orbital. Now dxz and dyz are very similar to this, except the one of the Cartesian axis is different. So this is the basis of crystal field theory as applied to an octahedral complex. So similarly, such splitting diagrams can be developed theoretically for complexes in tetrahedral geometry or square planar geometry, and various other geometries can be easily considered.